In this video, we'll talk about two more examples of the Galois correspondence in action. So first, we'll return to an example we've studied quite a bit already. Q adjoint square root of 2 and square root of 3 is Galois over Q. What is the Galois group? It's isomorphic to Z mod 2Z cross Z mod 2Z. We have one automorphism of Q adjoint square root of 2 square root of 3 that sends square root of 2 to negative square root of 2 and square root of 3 to itself. We have another one that sends square root of 3 to negative square root of 3, square root of 2 to itself. And then we have one that sends square root of 2 to negative square root of 2, square root of 3 to negative square root of 3. And then we have the identity one, and that's all of them. So if you take square root of 2 plus square root of 3, it's very clear that that's an element of this field. So that means that the field generated over Q by square root of 2 plus square root of 3 is contained in Q adjoint square root of 2 square root of 3. And in fact, we showed earlier that these two fields are actually the same. How did we do that? We showed that both of these fields have degree 4 over Q, and two fields of the same degree over Q, where one is contained in the other, are equal. How did we show that Q adjoint square root of 2 plus square root of 3 was degree 4 over Q? That comes down to asking, what is the degree of the minimal polynomial of square root of 2 plus square root of 3 over Q? So we had to find a monic irreducible polynomial satisfied by square root of 2 plus square root of 3. We could write down a quartic polynomial satisfied by square root of 2 plus square root of 3, but then we had to argue that it actually was irreducible. Okay. We now have some additional tools at our disposal. This field is contained in this field that is Galois over Q. Square root of 2 plus square root of 3 is an element inside this Galois extension, Q adjoint square root of 2 square root of 3 over Q. So a corollary of this thing that we called proposition 13 star, this condition that Galois extensions have that many other sources call the extension being normal, about every irreducible polynomial with a root in K has all of its roots in K. This corollary says that we know one root of this minimal polynomial is square root of 2 plus square root of 3. What are the other roots? They are the distinct Galois conjugates of this element, square root of 2 plus square root of 3. So we just apply each Galois element to square root of 2 plus square root of 3 and see what we get. And what we get is plus or minus square root of 2 plus or minus square root of 3. Okay, so that's 4 roots. And we just multiply x minus each of those roots together. And we see that the minimal polynomial is x minus square root of 2 plus square root of 3 times x minus square root of 2 minus square root of 3 times x minus negative square root of 2 plus square root of 3 times x minus negative square root of 2 minus square root of 3. It's a little exercise to see that when you multiply these together, what you get is x to the 4th minus 10x squared plus 1. And now we know for free that this polynomial is irreducible in Q bracket x because it is the minimal polynomial of this element. So what's the difference here is before, when we did this kind of argument, we had to work harder to figure out what the minimal polynomial was. Once we found even this quartic polynomial satisfied by square root of 2 plus square root of 3, we had to make a separate argument to say that it's irreducible. But here, this result, saying that the roots of the minimal polynomial are the distinct Galois conjugates of this element, tells us what the minimal polynomial is, and we know that it's irreducible. Okay, so that says that these two fields are equal because they're both degree 4 over Q. This part of the argument is the same. There's another way that we could conclude using the Galois correspondence. I mean, we could say that Q adjoint square root of 2 plus square root of 3 is a subfield of Q adjoint square root of 2 square root of 3. So under the Galois correspondence, this subfield corresponds to some subgroup of the Galois group. Which subgroup does it correspond to? Well, just apply each of the Galois elements to this element square root of 2 plus square root of 3, and you'll see that the only Galois element fixing this one element in this field is the trivial one. So you apply any of the three other Galois elements to square root of 2, square root of 3, and you get something different. You get a Galois conjugate that's not square root of 2 plus square root of 3. So the only subgroup of this Galois group fixing this entire field is the trivial, the only element of the Galois group fixing this entire field is the identity. So what does that mean? The subgroup of the Galois group fixing this field is the trivial subgroup. But the Galois correspondence says that there's this correspondence between subfields of Q adjoins square root of 2, square root of 3 containing Q and subgroups of the Galois group. And we already know which field corresponds to the trivial subgroup. It's the whole field, the one generated by square root of 2 and square root of 3 over Q. So here we found another field that is a subfield that corresponds to the trivial subgroup, so it must be equal to the whole field. Okay, so I'm going to pause and erase, and then I'll write down another example where we can look carefully at the correspondence between the lattice of subfields and the lattice of subgroups. Let's return to an example that we've talked about quite a bit already. This is something that's discussed really extensively in Conrad's The Galois Correspondence Notes. We have this field generated over Q by the fourth root of 2 and I. It's a splitting field for the polynomial x to the fourth minus 2. It's Galois over Q. And the Galois group we saw is generated by these two automorphisms R and S, and is isomorphic to the dihedral group of order 8, where, okay, what is R? R sends the fourth root of 2 to I times the fourth root of 2, and I to I. And S sends the fourth root of 2 to the fourth root of 2, and I to negative I. We can write down the lattice of subgroups of this dihedral group of order 8. And now we know by the Galois correspondence, for each one of these subgroups, we can write down the fixed field, and that's all of the subfields. That gives the whole subfield lattice over on this side. There's a lot more that we know now in this diagram, and I encourage you to really think about this. We can tell which extensions over Q are normal. Sorry, are Galois, by asking which of the corresponding subgroups are normal in this dihedral group of order 8. You can see this correspondence having to do with sizes. So we've written one subfield lattice looks like the other subgroup lattice turned upside down, this dual. Here we have subgroups of order 2. Here we have subfields where the degree of the big field over these subfields is degree 2. So here we have subgroups of index 2, and here we have extensions of Q of degree 2. So you should check that you really do believe the fields that I've written in here so far. I mean, for example, it's pretty straightforward to see that the fixed field of the subgroup generated by S really is Q adjoin the fourth root of 2. So this extension over Q is not Galois. This subgroup is not normal in this bigger group. But it's not always so easy to see how to fill in the lattice of subfields. So I've left these two blank for now. So there's some field F1 here. There's some field F2 here. We know this field F1 contains Q adjoin I times the square root of 2, and that it is the fixed field of the subgroup generated by the automorphism RS. But what is it? Like, how do we actually describe it? So that's what I'm going to talk about next. So I'm going to pause and erase. And the idea, the first thing we could do is something that we've talked about already. Like, we can see which elements of this big field are fixed by the automorphism RS by writing down a basis for Q adjoin fourth root of 2 and I over Q, and then just seeing how RS acts on an arbitrary Q linear combination of those basis elements. That'll give us this set of elements that make up the field F1. But then we can ask for more, like how do we give sort of a nice description of F1 as an extension of Q, what I mean is that, okay, this is a finite extension. It's generated by finitely many algebraic elements over Q. How do we come up with a good description of a generating set for F1 over Q? Okay, so I'll pause and erase, and we'll talk about this question. Let's continue our discussion of this example. We're trying to find the fixed field of the subgroup generated by this automorphism RS. So let's take an arbitrary element of our field Q adjoined fourth root of 2 and I. So every such element can be written as A plus B times the fourth root of 2 plus C times the square root of 2 plus D times the fourth root of 2 cubed plus EI plus FI fourth root of 2 plus GI square root of 2 plus HI fourth root of 2 cubed. This extension is degree 8 over Q. So it's an 8-dimensional vector space over Q. So let's just look at what RS does to this element alpha. You can check that I did this correctly. I mean, this example is taken from Conrad's notes, so you can check that I copied it correctly. So if you know what RS does to alpha, now we can determine when is alpha fixed by this automorphism RS, this automorphism of K fixing Q. Well, RS alpha equals alpha if and only if, well, for example, here we have F as the coefficient of I times the fourth root of 2. And when we apply RS, we get B I times the fourth root of 2. And then we don't have an I times the fourth root of 2 anywhere else. So we need to have B equals F. Similarly, C has to be equal to negative C. E has to be equal to negative E. D has to be equal to negative H. So C is 0, E is 0, D is equal to negative H, B is equal to F. You can see that this happens if and only if alpha is of the form A plus B times fourth root of 2 plus I times the fourth root of 2, B equals F, plus D times fourth root of 2 cubed minus I times the fourth root of 2 cubed, D equals minus H here. And then G can be whatever it is, plus G I times the square root of 2. Okay, so thinking about this, this is giving us a Q basis of F1, the fixed field of the subgroup generated by RS. We're getting 4 Q linearly independent elements of this big field K. So we're getting a description of this degree 4 extension of Q. Okay, the degree being 4 makes sense because this subgroup generated by RS has order 2 or inside D8 or index 4 inside D8. Okay, but maybe we want a nicer description of what this fixed field is than just it's all the elements of this form in terms of A, B, D, and G. So if we think about the subfield diagram and the corresponding subgroup diagram, we have the fixed field of RS. It contains this subfield that is the fixed field of the subgroup generated by RS and R squared. So if we want a description of this fixed field, one thing we can do is take an element that's in this fixed field, but not in this subfield of it that we do know a nice description of. So what are we looking for? We're looking for an element fixed by RS that is not fixed by R squared. If we can find such an element, then it'll be in the fixed field of the subgroup generated by RS, but not in the fixed field of the subgroup generated by R squared and RS. And at this point, most things you try will work. There's not like an obvious best choice of what to do. So you should just try something easy and see if it has this property. For example, I mean, if you set A equals 1 and everything else equal to 0, then you have something in Q. So it's actually fixed by all of the automorphisms. So don't do that. So maybe the next simplest thing you would want to do is, well, okay, what if you take like B equals 1 and all the other coefficients 0? So that gives alpha equals fourth root of 2 plus I times the fourth root of 2, 1 plus I times the fourth root of 2. Is that fixed by r squared? No. I mean, just apply r squared and you see what you get is alpha goes to negative alpha. So it's not fixed. So now we have this special element, and we know that this is fixed by Rs. It's in the fixed field of the subgroup generated by Rs. So if you take the field generated over Q by this element, Q adjoint alpha, this is contained in the fixed field of the subgroup generated by Rs. But it's not contained in the fixed field of the subgroup generated by R squared and Rs. So now think about what that means. So the subgroup corresponding to Q adjoint alpha is some subgroup of the whole Galois group, which is generated by R and S. And these two facts together tell you that the only possibility for where this field could sit in the subfield diagram is that it must actually be the fixed field of the subgroup generated by Rs. Okay, so we're seeing that using the Galois correspondence, understanding the relationship between subgroups of the Galois group and subfields of this Galois field extension, we can more easily do things like come up with nice descriptions of the fixed fields of the various subgroups.